All right, good morning, chemists. We'll get started here. Hopefully everyone had a nice, relaxing, warm weekend. I'll just up my microphone. All right. Okay, we'll get started here. Hopefully everyone had a nice, warm weekend and you didn't blow away. My power went out for like 2 days and it was awful. I came in yesterday. I don't usually come in on Mondays, but I had to because I had no power. So I couldn't do anything on the internet, and so that was pretty bad. My last ditch effort was to take a shower in like one of the buildings in case it didn't come back for class today, but it did come back. So that was an interesting weekend for me. All right, so we left off, we're at the end of chapter 19 here where we're talking about entropy and spontaneity and kind of unveiling the curtain behind some of the chemical processes that you just kind of trusted me happened. So we've been, studying a lot of different chemical reactions over the past year, and the reason why we see chemical reactions occur is because of Gibbs free energy. Reactions occur spontaneously when delta G is a negative value, and so we're relating this to concepts we already know, such as Le Chatelier's principle. If we have a system that's at equilibrium already, delta G is 0, meaning that the forward and the reverse reactions are likely to occur. That is equilibrium. But when we disrupt equilibrium, we apply Le Chatelier's principle. The quick and dirty way is, okay, if you add a reactant, the reaction shifts to the product side to make up for, that disruption in equilibrium. But really, the reason why that shift happens is because you change the sign of delta G. And so we're going through this example and relating it to something we've already discussed, and that's the idea of equilibria for saturated solutions. So here is the KSP for dissolving calcium hydroxide solid. We know that when you put solid into water, some of that solid splits up into its ions, calcium 2+ and 2 hydroxides. But if you look at the solubility table, you'll see that calcium hydroxide isn't super soluble in water, and so it has a fairly low KSP, meaning that you don't form that much products. And so based upon this value of KSP, that's the concentration of the ions at equilibrium, we can choose which delta G equation to use. And the thing to see here is that since you're given KSP, you want to use the delta G equation that has K in it. So we will want to use that first equation here to calculate what is the delta G naught for a saturated solution of calcium hydroxide. So that's what we did in this first part. We just plugged in that KSP value into that first delta G equation, and that naught indicates standard conditions, so 298 Kelvin. So I technically did not have to give you this 298 Kelvin temperature. You should know that that's what the temperature is if that little naught is present. And so we get that the delta G of this system, delta G naught, is a positive value, indicating to us that means that is this reaction spontaneous based upon delta G? No. So that means the forward reaction isn't going to happen, and that's kind of what we see in this KSP value. The forward reaction making the products it's not going to happen. So that's why K is really, really small. So that's delta G naught. All right, so that's at equilibrium. We have K conditions. But now what happens? Well, what if we disrupt that equilibrium? That's Le Chatelier. If we add calcium 2+, so we're adding a product, how does some of these values change at that moment when we disrupt the equilibrium? Only delta G changes. We can now calculate a delta G value because we're not at equilibrium conditions anymore. Delta G naught doesn't change. That's still, at standard conditions. That's basically a table value that's always true at that temperature. So for this example, let's disrupt the equilibrium and calculate a new delta G value. Not delta G naught, we are calculating delta G because we're not at equilibrium, standard conditions. So we will use this second equation, delta G at the new non-equilibrium conditions equals the delta G value we already calculated plus RT ln Q. Q meaning non-equilibrium conditions. So hopefully all of that rings a bell from earlier chapters. So I actually have to give you values of Q here, so let's make up a solution of a bunch of calcium, some hydroxide. What is the new delta G value? So since we are calculating delta G without the knot, we want to be using that second equation, delta G with no knot, plus the LNQ stuff. So our first strategy here is let's calculate Q based upon the information given. But that does require us to balance the KSP equation. A reaction's happening, so we need to balance it in order to get the K expression. So that's what I have up here, that the KSP equation is calcium 2+ concentration times hydroxide squared because of the coefficients in the balanced chemical equation. And then we calculated Q. And so just based upon Q, if this was chapter, I don't know, whatever chapter, if we compare Q to K, we should be able to predict which direction the reaction goes. So based upon those two numbers, so I'll star them right here, compare Q to K. Which way should the reaction go? Towards the products or towards the reactants in order to achieve equilibrium? This is review. Towards the reactants. And so how I think of it is Q is bigger than K. K is generally products over reactants. So if Q is bigger than K, we have too much products. Let's make some reactants to make Q smaller to achieve K. That's how I think of it within there. So yes, we should be able to predict that the reaction will proceed towards the reactant side. But let's prove it by actually calculating delta G now. That's the new part in chapter 19. So we have Q. We just want to plug this into reaction or equation number 2. All right, where we're going to calculate delta G equals delta G naught. We already calculated that up here. So positive 29.6 times 10 to the 3 joules. And again, usually when we calculate these, because of the unit of R, it will come out in joules. And we want that, we don't want delta G to be in kilojoules because again, R is in joules. So we want all those units to match. So times R, 8.314, times the temperature, it's still at 298. We didn't change the temperature at all. And then times LNQ, what we just calculated, 1.25 times 10 to the negative 5. All right, and so when you shove that into your calculator, all right, you see that this RT-LNQ term is equal to something like, I'll just have to calculate it. Okay, 8.314 times 298 times ln 1.25 e negative 5 is something like negative 27971 joules. And now we are subtracting that number from the original delta G naught. And so when we add those two numbers together, you get delta G is equal to positive 1,630 joules. All right. So what does this number mean? A positive delta G value means what? The reaction is not spontaneous. But what about the reverse reaction? The reverse reaction is spontaneous, meaning that this reaction, it's not going to proceed forward, it's going to proceed in the reverse. Is that what Le Chatelier's principle, is that like the conclusion we came up with when applying Le Chatelier's principle? Yes, we saw that Q was bigger than K. The reaction has to go in reverse. That's exactly what delta G predicts. And so the reaction will proceed in the reverse direction until concentrations, your Q value approaches K. Once Q approaches K, then you're at equilibrium again. Delta G will be 0. You'll essentially achieve delta G naught conditions. That's essentially what that means. And then at that point, when delta G is 0, then the forward and reverse reactions happen at the same time, basically describing equilibrium. All right, so let's do one more example. So here it's the same exact question, but I give you just different concentrations. So it's the same strategy. Let's calculate Q.
all right, is calcium 2 plus concentration, so 0.012 molarity, times hydroxide concentration, 0.024 molarity, but that is squared. And so we get Q is equal to, let's see, 6.9 times 10 to the negative 6. That is Q. All right, so let's compare this Q to K. So compare this Q to K. They're basically the same number. I mean, Q is just like a tiny, tiny smidge bigger, but they're basically the same number. So what does that mean? If this was Le Chatelier's principle, if Q is equal to K, what does that mean? The system is it going to shift left? Is it going to shift right? It's already at equilibrium, so there's no shift. So let's prove it now. If we do this calculation, we're gonna shove this number back into our second equation here, our delta G equation, that second one. So delta G is equal to delta G naught, which we already calculated, so 29.6 times 10 to the 3, plus 8.314, that's R, times the temperature, 298 Kelvin, times natural log of 6.9 times 10 to the negative 6. But again, that Q is really, really close to K. We should already be at equilibrium conditions. And so when you put that into your calculator, you do get a really, really small number. I think when you put all of that into your calculator, you get negative 29439, and you essentially get a number that is very close to 0 joules, very close. So when you see that, that means that there is no driving force for the forward or the reverse reaction to occur at all. You're already at equilibrium conditions. The forward and reverse reactions are both happening, right? Because we don't have a positive delta G or a negative delta G, so there's no push for, one forward or reverse reaction. All right, so that is relating Q and these delta G, these new delta G equations not at equilibrium conditions to help relate it to something we already know, Le Chatelier's principle. All right, and so yeah, the idea here is when Q equals K, delta G is 0, but delta G naught still stays the same because those are basically table values. All right, so that's putting it together with something we already know. All right, so let's do this last example here, putting all of these things together. So here's another equation. In the previous question, we looked at solubility, so KSP, yeah.
In the last question, when you calculated, get that delta G is equal to 160, so like how close to 0, like, do you go when you say that?
How close? Well, so how I know that this system is at equilibrium is because Q is very, very close to K. I should have given better numbers that actually give a Q that's really close to K. But in the first example that we did when we used this second equation, Q is obviously much larger than K because the magnitude is different. Really, I should pick better numbers that make this exactly 6.5. That's what I was trying to get at here. All right, okay. But good question. All right, so let's put all of this together but study a different question or a different equation. We did KSP in the previous one, but let's look at the decomposition of lead carbonate to lead oxide and CO2. So using the provided data, and I have all these equations here. We might not use all of them. I want us to think about which equation we'll use because you will be given all of these equations. You just need to know which one to use. Let's calculate the equilibrium pressure of CO2 in this reaction at standard conditions, so 25 degrees, 298 Kelvin. So let's first look at this equation or this chemical reaction, and let's get K, because we know that we've been studying K and how it relates to delta G. What would the Kp for this reaction be? So this is a little bit of review. What does Kp mean? What does P mean? Pressure, yeah. So we need to get the equilibrium expression, but we want things to be in pressures. So at equilibrium, what do we care about? The pressure of what? CO2. Anything else? No. That's good, because this question is asking us, what is the equilibrium pressure of CO2? And it's equal to K. So that means if we calculate K, we get the equilibrium pressure of CO2. So that's nice because we do not include the solids in the K expression. Great, so if we calculate K, we get pressure of CO2. Okay, so let's look at the information that's given here. I give you delta G values for the reactants and products. So to me, it looks like I want to calculate delta G naught of this reaction. I'm calculating delta G naught because it's table values. These table values are at standard conditions, so we're calculating delta G naught. So looking at these equations, I'll just number them, 1, 2, 3, which equation do we want to use to get to our answer? Our goal is to get pressure of CO2. Which equation do we want to use? The first one. The first one because that's the only one that has K in it. So K is related to delta G. Can we calculate delta G? Yes, we can, using the table values. So that's the strategy here. Let's calculate delta G of the reaction first, doing products minus reactants, and then plug it into that first equation to calculate K. K is equal to the pressure of CO2 at equilibrium. All right, so products minus reactants. Products minus reactants. We've done this a billion times. All right, so here are my reactants. There's my product, so I'm going to add up the two yellow values and subtract the pink value. So negative 394.4 plus negative 187.9. Everything's a one-to-one stoichiometry, so that's nice. Minus negative 625.5. And all of this will be in kilojoules per mole. So negative 394, I think that, didn't I write it down? Did I write it down? Yes, so I get positive 43.2 times 10 to the 3 joules. I'll put joules per mole. All right, so based upon this number of delta G of our reaction, is this reaction spontaneous or not? No, not really. So does that mean this reaction will make products? No. So does that mean the pressure of CO2, will it be a big number or a small number? It's going to be rather small because the forward reaction doesn't proceed forward. So the next step here is, okay, now let's use equation 1 and plug in that delta G value to calculate K. And again, our intuition should say that K should be a small number. Yeah. It would be in, you're right, it is in, I think I skipped a step. I think when you do this, you get 43.2 kilojoules, but then I converted it into joules because I need it to be in joules for the next step. Yeah, so sorry, I skipped a step. So yeah, when you calculate it, because these table values are in kilojoules, so thanks for pointing that out because I skipped a step. When you calculate it, you get it in kilojoules, but I just took an extra step to convert it to joules because in reaction or equation 1, R is 8.31 for joules, and so that delta G value needs to be in joules in order for all of that to work out. You don't want to leave it in kilojoules. All right, okay, so the next equation, so delta G equals R negative R T ln K, so positive 43.2 times 10 to the 3 joules per mole of reaction equals negative 8.314 joule mole Kelvin. So I'll put my units so you can clearly see. Times temperature. What's the temperature? 298. Yeah, I told you that it's 298, and we should know because of that delta G naught there. So 298 ln K. All right, and so when you calculate ln, oh yeah, so my answers are all down there. When you calculate K, that's what we're solving for. Remember, K in this example is the pressure of CO2, and you get the number there that's in the corner, and you see it is a rather small number. All right, so I have both delta G naught that we calculated from products minus reactants, and also the K by using that first equation. Yeah. A big delta G, you mean like a delta G that's spontaneous? It would be a negative value. Yeah, so here it's a positive value, so we know that there is no driving force for the reaction to go forward. Does that make sense? Yeah, okay. Okay, So there's that one. And yeah, and so our intuition was right, that the equilibrium pressure of CO2 is super, super, super small. This reaction does not proceed forward, meaning that this reaction does not produce product, or it means that lead carbonate, if you just have it sitting on the shelf or on the table here at standard conditions, 298, it's not going to spontaneously decompose to CO2 at room temperature or at 298 Kelvin. So now what we're going to look at is, well, what if the temperature is not 298 Kelvin? Yes. Okay. So let's use the same data, okay, these thermodynamic quantities. We want to calculate the equilibrium pressure of CO2. Oh wait, sorry. So in this example, we're actually calculating the exact same thing. Okay, it's the same exact question, but I'm giving you different information. So see, in this question, I gave you delta G formation values. We just did products minus reactants. We got delta G. We wanted to use that first equation. But in this example, do I give you delta G values? No, I don't. I actually give you delta H and entropy values, but we can actually still solve this, this question. So I'll just number these reactions here again. All right, so using the provided data, we're still calculating equilibrium pressure of CO2, but I give you delta H and delta S values. So I can't actually calculate delta G directly, but there's another equation here that can allow me to calculate delta G naught. And which equation is that? Equation 1, 2, or 3? Number 3. And so with these two columns, I'm able to calculate, delta H and delta S of the reaction. And now I just need the temperature in order to calculate delta G. What is the temperature? 298, because we're still at standard conditions. So this question, it's just kind of a longer way to get to the answer. All right, so my strategy here is I actually want to calculate delta H of the reaction, and I want to calculate delta S of the reaction, again, products minus reactants, and then plug that into equation 3, and we should actually get the same delta G value that we got in the previous slide, and then, plug that into that K expression, or the K equation. All right, so this is just a longer way to get to the same answer, because I want to show you here that delta H's and delta S's, they are related to delta G. All right, so we're going to do products minus reactants, but we have to do it twice. So CO2 and lead oxide are our two reactants, and then lead carbonate is our reactant. So products minus reactants. So delta H of the reaction will just be negative 393.5 plus negative 217.3. minus negative 699.1. And all of this is in kilojoules, and I think I have the answer down there. This reaction is endothermic, so 88.3 kilojoules per mole of that reaction. That is delta H. Okay, just products minus reactants, make sure the unit you're using is correct, and in the table it's kilojoules. Because when we do the same thing for delta S of the reaction, products minus reactants, it comes out to joule Kelvin, not kilojoule. Thankfully, these numbers are all positive. I like calculating entropy changes because you're always working with positive numbers. I don't like negative numbers. 131, there's my reactant, and then you get a number like this, 151.3 joule. The unit here is wrong in the key. There should be a Kelvin down there. Mole Kelvin. Would we have, the sign of delta S of this reaction, it's positive, meaning that the reaction is gaining entropy. Would you have predicted that based upon the balanced chemical equation? Would you have predicted that entropy increases? Yes, because we're gaining gas particles. Yes, so entropy should be positive. Great. So we have delta H, we have delta S of our reaction. All right. So we're one step, not quite there yet. In order to calculate equilibrium pressure, or K in this case, we need delta G. We have not calculated delta G yet, but I want to prove to you that if we use these two pieces of information we just calculated and plug that into delta G equals delta H minus T delta S, we will get the same delta G we got in the previous slide, which is really great. But again, we want to make sure that our joule units match here or we'll be in trouble, all right? So let's plug in those values. 88.3 kilojoules per mole minus the temperature. What's the temperature here? 298 Kelvin, because that's what I told you, all right? So we're calculating delta G at 298 Kelvin, and then times delta S of the reaction. So do make sure you need to change one of them. I'll change delta S to 0.1513 kilojoule mole Kelvin. All right, and so when you calculate this delta G naught, I'm going to put the naught there because the temperature is 298, we actually get 43.2 kilojoules per mole. Right, and that is the exact same value we got in the other slide. So that's the neat thing here. With these thermodynamic quantities, you can calculate delta G different ways. I didn't give you delta G formation values, but you could have used them if you were given them. You can do products minus reactants. Or you can calculate the delta G value given delta H and delta S information as well. So we get to the same point. And so we have the delta G value like we got in the previous slide. So we just have to take it one step further and plug that into our delta G equals negative RT ln K. But you get the same answer as we got before, so I'm not going to do it. All right, so two ways to get the same answer. All right, so I want you to know the strategy here because we could ask you equilibrium concentrations, either giving you delta G values like the previous slide, or we can give you delta H and delta S values. So that requires you to go one step further, do one extra step where you use this delta H minus T delta S equation, and then plug it into that first equation that relates it to K. All right. So this one's a little bit harder. This one's a little bit harder. But the great thing here is once, in previous slides, we talked about the significance of delta G, delta H, and delta S. We said previously that delta G values do change significantly with temperature. All right, so when you change the temperature, you know, the delta G values on these tables no longer are valid for delta G. But we make an approximation where we say delta H and delta S values do not change with temperature. So if we know delta H and delta S, we can actually calculate delta G for any temperature. And that's what we're going to do in the next slide. All right, using all of this information, let's calculate the equilibrium pressure of CO2 again, but not at 298 Kelvin. This time, let's do it at 473 Kelvin. All right, so we're no longer at standard conditions. So can we use these delta G of formation values? No, we can't. We cannot use them. So instead, we're actually going to use the delta H and delta S values instead. We're going to use equation 3 to calculate, okay, what's the delta G at this temperature, assuming that delta H and delta S do not change with temperature, and then plug in that delta G value into our negative RT ln K. All right, so we should be getting a different delta G value in these examples because they're at different temperatures. All right, so we actually already got delta H and delta S in the previous slides, so I'll just write those down. Delta H of this reaction is equal to 88.3 kilojoules per mole. And again, my unit here for delta S is incorrect. There needs to be a Kelvin. Delta S of this reaction is, I'm just going to put in kilojoules, 0.1513 kilojoule mole Kelvin. All right, and our temperature is equal to 473 Kelvin, not standard conditions. All right, that's why we cannot use the delta G of formations with the naught, because we're not at 298 Kelvin. All right, so we're going to use the delta H and delta S values instead. So we're going to use equation 3 here, where delta G is equal to delta H minus T delta S. We'll plug in all those numbers. We have delta H, we have delta S, and I told you a new temperature. So we should get a different delta G value. All right, this is equal to 88.3 kilojoules per mole, I'm just gonna drop the unit, 473 Kelvin times that delta S value, 0.1513 kilojoule Kelvin. And so we get a number like, where is it? 16.73 kilojoules. This is delta G. And note how I didn't put delta G naught, because this delta G is not at standard conditions. It's at a different temperature, so I'm not putting the naught there. All right, so here's a different way to calculate delta G. But based upon the value, is the forward reaction very spontaneous? No, because it's delta G still a positive number, so we should still get a very small number for the equilibrium, our K equilibrium. So this is the value we want to set equal to negative RT ln K and solve for K. And remember at the beginning here that we related K to the equilibrium pressure of CO2, so that's a small detail there. So if we calculate K, we will get the equilibrium pressure of CO2. So let's put it all together here. So per mole, delta G is equal, I'm gonna convert it to joules so I can stick it into this first equation, all right? So I'm using equation 1 here, so 16.73 times 10 to the 3 joule per mole equals negative R 8.314 joule mole Kelvin times temperature. What temperature do I put here? The 473, because this is at a different temperature. So 473 Kelvin times ln K. And so we are calculating for K. K is equal to our equilibrium pressure of CO2. And so when you solve for this, you get that K is equal to, so if you do all of that math, you're taking, you're undoing the natural log. It's e to the negative 4.25. That's what all of that math stuff, when you put all of those numerical values together. So you get that K is equal to, it's still a rather small number, but bigger than at room temperature. You get that K is equal to, oh, it's right there, 0.014 ATM. And that is our equilibrium pressure of CO2 at 200 degrees Celsius or 473 Kelvin. Okay, so it looks like there is more CO2 at equilibrium when we're at a higher temperature. All right, there's small details that I can actually relate this to in Le Chatelier's principle. Is this reaction exothermic or endothermic? The answer is actually on the board. Endo versus exo means the sign of what value? Delta H. Didn't we already calculate that? Ah, yes, we already calculated. So now tell me, is this reaction endo or exothermic? Endo. So is triangle a reactant or a product? If heat is if we treat heat as a reactant or product, where does it go? Reactant. So if this was Le Chatelier's principle, and I told you just to do the quick and dirty way to predict shift, if you add heat, if you add triangle to this reaction, which way does the reaction shift? To the products. Is that what we predicted also with calculating delta G? Yes, unfortunately. We calculated that at equilibrium, at a higher temperature, all right, that there's more CO2 at equilibrium versus at room temperature. So basically what we calculated fits exactly with Le Chatelier's principle as well. All right, so let's do this calculation again, but at 600 degrees Celsius. So just using your Le Chatelier, intuition here, should the equilibrium pressure of CO2 be higher or lower than what we just calculated? Even higher, yeah, because this is endothermic, triangle is a reactant. We're adding more triangle, a reactant. It's going to push it to products. So there should be even more CO2 at equilibrium. So let's just go through the strategy again. Is 600 degrees Celsius at standard conditions? No, it's not. So can we use delta G formation values on the table? Can we use these? No, we can't. So we have to use delta H and delta S of the reaction instead. I gave you the, the reactants and products, so you can do products minus reactants. But in exam questions, I could also just give you delta H reaction and delta S reaction straight away. That's another way to make it a little bit easier. So I want to use these two values to calculate delta G at 873 Kelvin. So I'm going to use this third equation, delta G equals delta H minus T delta S. All right, so 88.3 minus the temperature we're at is 873 Kelvin times delta S, but in kilojoules, so 0.1513. And so I get that delta G at 873 Kelvin is equal to, I have it here, negative 43.78 kilojoules per mole. So based upon that answer here, is this reaction spontaneous at 600 degrees Celsius? Yes, it is. So will we have a lot or a little CO2 at equilibrium? A lot. We should have a lot. K should be a really large number. All right, and so we calculated delta G. We want to plug that into not reaction 3, but equation 1 in this case. But do make sure delta G is in joules instead. So negative 43.78 times 10 to the 3 joules equals negative R 8.314, temperature 873 times ln K. And then when we solve for K, all right, we do in fact get a large number. So there's the last equation we get. And remember, K is equal to the equilibrium pressure of CO2. Oh yeah, and you get a really large number, 416 ATM. So yeah, we have a hecton of CO2 at equilibrium because now delta G at this temperature is a negative value. The forward reaction is spontaneous. So basically, if there's any summary of the last couple slides, is that if you're given table values, thermodynamic values, and you have to do products minus reactants, when you're working with delta G, you can only use those delta G table values if you're at 298 Kelvin. If you're not at 298 Kelvin and you want to calculate the delta G at any other temperature, you actually need to use delta H and delta S of the reaction to predict what the delta H of the delta G at that temperature is, and then plug it into any corresponding equation. And so the interesting here with these examples is we did not use the delta G equals delta naught plus RT ln Q. We didn't use this equation because Q, is that equilibrium conditions? No, Q is non-equilibrium conditions. So since this question is asking for equilibrium pressure of CO2, we can go ahead and use that first equation because that's where K is. We're at equilibrium. We just have to do some futzing around and some massaging to get the appropriate delta G, depending on what temperature it's at, all right? Because I think the most common mistake for these kinds of questions, if I provided you this question, what a lot of students will do is use the table values to calculate delta G. They'll plug it into equation 1 and they'll put the temperature as 473 or whatever, or whatever temperature it is, and calculate K. We can't do that because delta G does change with temperatures, but we're making the approximation that delta H and delta S do not with temperature. Yeah? Why are we allowed to plug in for delta G of formation? So these formation values are for the formations of these specific substances. We're actually not plugging in any of these numbers directly into these equations. We're first calculating the change in the reaction. So we take these numbers and do products minus reactants first. So that's how we get our delta G of our reaction. So this delta G is not delta G of formation. This is the delta G of the reaction because we're relating it to the delta H of the reaction and delta S of the reaction. That is also not delta G of formation. This is also, all of these delta Gs are delta Gs of reactions. Yeah. Okay, the only delta G's or delta H's of formation you see are on these table values. We never put these table values directly into any of these equations. We do the products minus reactants first to get the appropriate delta letter reaction. Does that make sense? Okay, great. And then your question? It does, yes. Delta G does change according to temperature, but we need to make sure we're using the appropriate delta G. So in that equation, see how there's a knot there? There's a knot there. So if we were using delta G knot, so from the, we do products minus reactants from the table values, T would be 298. But you can also use the same equation if it's not at 298. It wouldn't be, it would be like delta G with no knot. You use the appropriate temperature, but you have to use equation 3 first. So you use the same equation. Really, I shouldn't have the knot there. It's the same equation whether it's not or not. Okay, yes, there's a lot going on here. Okay, so let's summarize everything, okay? Spontaneity, let's think about the signs, all right? You've come a long way. We've gone through all these letters, all right? So enthalpy, review of 1210, enthalpy. Endo versus exothermic reactions, the sign of delta H, all right? Exothermic reactions, the ones that we love because they give off a lot of energy. We, as the surroundings, see that energy. That is a negative sign of delta H, right? Exothermic reactions. So I like to think, okay, triangle is a product, and that's what we see as the surroundings. Endothermic reactions, triangle is a reactant. All right, that you have to put energy into the system in order to get the reaction to go. All right, so these signs, they have significance. All right, so second law of thermodynamics says that when the entropy of the universe increases, a reaction is, or a process is spontaneous. Only when, again, entropy of the universe increases. We can track the entropy changes of the system and the entropy changes of the surroundings. And so as long as one of them is fairly positive, more so than the other, typically a reaction is spontaneous. So what we'll see here is that if reactions are highly exothermic, they're usually spontaneous because delta S of the surroundings becomes a very positive number. All right, so that's the second law of thermodynamics, but it's hard to track the system and the surroundings at the same time. So oftentimes we talk about free energy instead, which already includes delta H and delta S incorporated into it, but it focuses solely on the reaction. We don't have to take into account what's happening with the surroundings. And so with free energy, do recognize delta G naught means at standard conditions. Typically it means 298 Kelvin. It's fine to use table values there. But when we have delta G, no, I didn't just forget the naught. I am very explicit which term I use, means at non-standard conditions. So it's typically not at 298 Kelvin. All right, so if I number these equations, all right, if we are given, if we're at standard conditions, it's quite okay for us to use equation number 1 if we're already at standard conditions. But if we're not at standard conditions, we typically have to use equation 3 first to calculate delta G, and then we can use equation 1. All right, because we have, as long as we know the delta H and delta S values, we can plug in the appropriate non-standard condition temperature to calculate the delta G at that instance. And so regardless if we are using any of these delta G equations, even this, oh sorry, I numbered these the wrong way. So I'm gonna call this equation 3 just to mimic what we were doing in the previous slides. I called this equation 1 and I called that equation 2. I don't know why, that's the order in the previous slides. So again, you use equation 3 first, where we're making the approximation delta H and delta S stay constant with temperature, so we can calculate delta G at any temperature, all right? Because remember, we use that equation to predict the melting and boiling points of substances, where we said, okay, the melting point of a substance is when the solid and the liquid are at equilibrium. We set this equation equal to 0 to calculate the melting point temperature. We're basically doing the same thing with those previous examples as well, calculating delta G at different temperatures, but assuming delta H and delta S of the reactions do not change with temperature. And then if we actually want equilibrium conditions, we plug equation 3, the answer to equation 3, into equation 1 to calculate K. But regardless of what equation you use, delta G, depending on the sign, tells you what conditions that reactions are under. If it's already 0, it means you're at equilibrium. If it's a positive number, it means the forward reaction is not spontaneous, so that means the reverse reaction is actually spontaneous. But if delta G is negative, the forward reaction as written is the spontaneous reaction. All right, so that's putting it all together and applying it to Le Chatelier's principle. All right, so that is, reaction spontaneity, okay? Okay. So do make sure, are you at standard conditions? Are you allowed to just use the table values? Is it delta G naught that you're calculating, or is it just delta G? All right, so the last part of this chapter talks about thermodynamics and kinetics. The main idea in this part of this chapter is, yes, we looked at a bunch of reactions that were spontaneous. Delta G is negative, but it doesn't quite mean that those reactions are fast, because fast refers to what? Chapter 14, we talked about chemical kinetics. Fast, reactions going fast means they have a large K, rate constant. So rate constant, small k, yeah, small k, you remember that guy? Small k tells us whether a reaction's fast or not. Small k is not embedded in any of these delta G equations. We only get equilibrium constant, big K. So again, rate constant is related to, you know, your free energy diagram and activation energies of the actual chemical reaction that is happening. Let's remind ourselves what the trend is. So reactions are fast, or rate constant is large when activation energy of your process is small, yes. What's another way to increase rate constant? Temperature, yeah, if we increase temperature, then the rate constant increases as well because of the Arrhenius equation. So again, just because a reaction is spontaneous, so in this example, delta G is a negative value, doesn't necessarily mean the reaction is fast. It can, but it doesn't necessarily mean that. So in this reaction here, the really exothermic reaction of combustion of thermite. All right, you can see, okay, delta G is really, really negative. This reaction is actually very, very fast. It just so happens to have a very negative delta G value. But we'll look at some examples where that's not necessarily true, right? So here I wanted to rant about diamonds again. All right, so let's look at some other spontaneous reactions, and I already have this calculated for you. If I take diamond, okay, so like carbon solid, but diamond, add oxygen and I produce CO2, what kind of reaction is that? Combustion, yeah. We're taking diamond, or if I had infinite money and then I added oxygen and combusted it, the only product is actually CO2. So we can actually calculate the delta G of that reaction, and let's see what it is. So to calculate delta G of this reaction, we take products minus reactants. I have those values down there. So we're going to assume it's at standard conditions, so we don't actually have to use delta H or delta S values. We can go ahead and just use the delta G values of formation. So I already did the calculation for you where we are taking CO2, that's our product, and we're subtracting the two reactants, so O2 and diamond. And we see that O2 is already in its most stable state, so that has a free energy of formation of 0. So CO2 minus diamond, the combustion of diamond is almost negative 400 kilojoules per mole. So is this reaction spontaneous? If delta G is negative 400? Yes, it is. So if I took a diamond and I lit it on fire, it would happen. It would happen at room temperature, so at standard conditions. So it would, in fact, light on fire. Yes, it would, because delta G is negative. So let's look at another reaction. So here is combustion of diamond. Yes, combustion of basically any, carbon-containing thing is spontaneous at room temperature. So let's look at this reaction, the conversion of diamond to graphite. Oh, and let me ask you, are combustion reactions typically fast or slow? They're pretty fast, yeah, they're pretty fast. So this is actually quite fast. But let's look at this reaction, the conversion of diamond to graphite. So we're going to do products minus reactants again and calculate delta G. The free energy of graphite, again, from this table is right here, is 0. And we're subtracting the free energy of diamond, our reactant. So products minus reactants, 0 minus 2.8 kilojoules per mole. So I get that the energy change of the conversion of diamond to graphite is -2 kilojoules per mole. So based upon this number, is the conversion of diamond to graphite spontaneous? Yes, it is. Yes, that over time, given enough time, diamond will spontaneously convert to graphite. But using your basic human knowledge, does that happen fast? No, because what does the De Beers company say about diamonds? Diamonds are forever. So are they, in fact, are diamonds forever? No, they're not, because delta G of the conversion between diamond, carbon solid diamond, to graphite is actually a negative value. So diamonds are, in fact, not forever. But is this conversion fast? No, it's not. But us just looking at this delta G value, I can't make that conclusion, right, based upon that. I just want you to associate that, hey, you know, just because it's spontaneous does not mean that the reaction is fast. And so let me show you an example, and this is the last slide here. All right, so yes, is it spontaneous? Yes, but is it fast? No. So this is kind of what's happening on a molecular level. Diamond, you know, we have the SP3 hybridized carbons. Every carbon is bonded to another carbon. Graphite, on the other hand, is more stable than diamond, but because they're in these pleated sheets, you know, a lot of bond breaking has to happen. Although it is spontaneous, it is not super fast because a lot of bonds have to break, essentially. But given enough time, if we're on this Earth for a very, very long time, yes, we will see all the diamond on Earth convert to graphite. Yes. All right, and so here's an example. Just because it's spontaneous doesn't mean it's fast. Fast refers to K and equilibrium activation energy from chapter 14. So in this example, all right, this is a negative delta G value, so this is spontaneous. But if the activation energy is really, really, really large, all right, like our conversion of diamond to graphite, lots of bonds have to be broken. You know, our system can't go over this initial activation energy hump, so it isn't super likely, and it's not very fast that anything will be converted to the other side. So just because it's spontaneous, again, doesn't necessarily mean it's fast. We actually have to relate it to our activation energy. Okay, so yeah, diamonds aren't forever. Yeah.
So what about, like, in chapter 12, you talked about your wedding ring?
Yes, my wedding ring.
And then you also talked about the others, like...
Oh, the diamond alternative,
Yeah.
moissanite?
Yeah, does that one convert over time?
Well, so, okay, so the question is, so diamond, yeah, carbon, solid, diamond goes to carbon, solid, graphite over time. Yes, that delta G is negative. So the question is, I don't buy diamonds for philosophical and thermodynamic reasons, but my wedding ring is made of moissanite. So it's actually silicon carbide solid. So because it's compositionally different, we cannot make the same like comparison because there's silicon in there as well. So I don't know, I'd have to look into it. Like, would this convert to just, you know, free carbon, you know, graphite and like free silicon? I'm not sure, I'd have to calculate it. We can calculate it in office hours. Okay, very good, yes. How long it would take to convert diamond to graphite? I'm not sure. We'd have to look at an energy diagram to see the activation energy. Yes. Maybe we can look it up in office hours. Yes, okay. Great. So there we go. There's our second law of thermodynamics. Hopefully you like entropy. I think it unveils a lot about our observations and you know, things that we take for granted. Okay, all right. So we will move on to we will move on to electrochemistry. Yay, yes. I like electrochemistry because, I don't know, it's very different than anything we've learned thus far in 1220. Yes, so if you don't like K, we're going to put it in our back pocket for a while for electrochemistry, but it's actually going to come back out again. All right, and if you didn't like thermodynamics, delta G is going to come back out at the end of this chapter, but we'll look at electrochemical processes. We'll revisit things like 1210 concepts. Do you remember the activity series? Right, where if you put a magnesium strip in acid, it spontaneously dissolves and you see bubbles form. We're going to answer why that happens. Why does anything happen? Because delta G is negative. Yes, and that basically explains our world. The reason why things happen is because delta G is negative. And related to electrochemistry, all right, reactions happen when delta G is negative. When we set up electrochemical cells, when the cell potential of your cell you set up, when it's a positive value, you also have a spontaneous reaction. These two ideas, the cell potential of your cell and delta G of your reaction, is related by an equation that has a negative sign embedded into it. So again, you know how we related big Ks to very negative delta Gs? We also can relate to cell potentials when we set up some electrochemical cell with an anode and a cathode. So we'll go through all of those things. So in the back of your mind, just memorize this. Your anode has oxidation. Oxidation occurs at your anode. Reduction occurs at your cathode. So just memorize that. So I memorize it, N-ox, red cat. And that's basically 50% of this chapter. So we're going to review some concepts, all right? So do review some of these things, but we're going to take some time and do that review, right? So electrochemistry is very different than anything we've talked about previously, but electrochemistry, I think in this day and age and technology, is one of the, most important and most utilized forms of chemistry, all right? Honda is building a new battery plant in Grove City. They just broke ground on it. I think there's a very high chance that someone in this room will work at that Honda plant. All right, that it's like a $5 billion project, and it's going to be in Columbus. Or Intel moving one of its semiconductor manufacturing plants in New Albany. All right, so this is like really cutting edge things that are utilized in society today. And I think this chapter is very important there. So we're going to be setting up some electrochemical cells. How do we make electricity? We'll look at batteries and kind of dispel this myth of, you ever see this demo in high school where they put like the nails in the potato and they light the light bulb, and then, kids are stupid, so they think that potatoes can just have electricity. They don't. Okay, potatoes don't have just contain electricity. It's actually a electrochemical reaction that's happening here, all right? But kids are stupid, so they think that just potatoes have unlimited energy. So we'll explain it. All right, so we need to review some ideas from earlier chapters, Chem 1210, redox reactions, oxidation states, so let's review that, all right? So this was from 1210. And if you didn't take 1210 here, that's fine. We'll do enough review that you'll be fine. All right, so this is like a 1210 question. All right, here is a chemical reaction. It's a single displacement reaction. Does that ring a bell? Single displacement. I can ask these types of questions. Is this reaction spontaneous as written? So really, what is the question asking? Is delta G negative? Yes, right. But we're smarter, all right, now, okay? And we can relate it to delta G. I can ask, what is the net ionic equation? We'll go over that. What element is oxidized and reduced? And then finally, what is the oxidizing agent? What is the reducing agent? So here is the activity series. This allows us to predict whether something's spontaneous. We can write out the net ionic equation. Once we have oxidation numbers, we can figure out what's oxidized and what's reduced. So we'll come back to this. Let's just review all the things we need to know before we can answer the question. All right, oxidation numbers. All right, basically, if you think charge, that'll get you 95% of the way there. All right, so here are the rules for oxidation numbers for elements that are in compounds. So when you see elements in balanced chemical equations, you can figure out their oxidation numbers. In redox reactions, electrons are being transferred, so we need to look at the charge of our products and our reactants to determine what is being oxidized, what's being reduced. So here are the rules. The first one is if you see an element in its elemental form, all right, then the oxidation number is 0. Or I like to think, okay, all of these elements are just neutral. Neutral means 0, right? So the oxidation numbers are 0. So here are just some examples. This is not an exhaustive list, but the commonality here that all of these elements, they're just elements in their neutral state. So like oxygen gas, hydrogen gas, iron solid, aluminum salt, etc. Once we start putting substances in compounds, all right, we need to be thinking charge. Compounds have an overall charge of 0, and what we see is that the sum of oxidation numbers will always equal their charge, all right? So yeah. Then the second one here, oxidation number of something that is charged, something that is ionic. Typically, its oxidation number is its charge, all right? So again, if you think charge, it'll get you 90% of the way there. So silver plus, what is its oxidation number? Don't think about it too hard. Charge is oxidation number. +1. What is zinc 2 plus? +2. What is iron 3 plus? +3. What is chloride minus? -1. Great. But what would chloride 2 be? Cl2 gas. What would the oxidation number of that be? It would be 0, yes. So if we had chloride convert to Cl2, we see its oxidation number changes. And that's what we track in redox reactions. All right, and then so points 1 and 2 will get you like most of the way there. Sums of oxidation numbers in compounds will always equal its overall charge. So that's a nice way to predict oxidation numbers of things that you might not really know what the oxidation number is. You can kind of calculate it. So for example here, iron 3 chloride. There's 3 chlorides there. So each one of those chlorides are -1. And so if you remember your naming, like ionic compound naming, this will help you as well. It's kind of in that same category. So since there's 3 chlorides, what does the charge of iron have to be? +3. And so that is iron's oxidation number there. All right. And so iron is +3. Each of those chlorides is -1. Again, thinking charge gets you halfway there. All right, but in this example, nitrate, all right, nitrate, it's not super obvious what the oxidation number of nitrogen is, but we use the tip here in the next thing. Oxygen is almost always O2 minus, except in oxygen gas. So we're going to use that tip to get NO3 minus. So if oxygen is -2 and there's 3 of them, what does the oxidation number of nitrogen have to be? +5. Yes, it has to be +5 in order for all those charges to work out. All right. And so, yeah, basically think charge. Oxygen is almost always O2 minus in a compound. And hydrogen is almost always +1 when it's attached to a nonmetal, which is most of the examples that we'll have here. Hydrogen can also have a -1 oxidation number, but that's only when it's attached to a metal like lithium hydride. We don't talk about hydrides often. I just want to show you it, but we don't typically run into this example. Except when hydrogen's a gas, because then what is the oxidation number here? It is 0. All right, so that helps you with oxidation numbers. Let's go through some examples. Again, if you think charge, you will most likely be right. So what is the oxidation number in hydrogen gas? 0. Bromine in bromine liquid? 0. What about H and B and HBr? +1 and -1. Again, thinking charge gets you there. All right, that if this HBr aqueous, that's a strong electrolyte, it's a strong acid. So if you put that in water, you have H plus and Br minus. So if you think charge, you can also get oxidation number. All right, so those ones are rather easy. Now it gets a little bit harder. Calcium and chloride and calcium chloride. +2 and -1. Yes, because there's 2 chlorides, those 2 negative oxidation numbers add up, cancel out with the calcium 2+. Chromium and oxygen. Yeah, so remember here, so this one's a little trickier. So remember, oxygen is almost always what? -2, yeah. And so since there's 3 oxygens, that's a total of -6. So I need a +6 coming from chromiums, but there's 2 of them, so each chromium is what? +3, yeah. And again, if you think charge, it's like the same answer. All right. Okay, manganese in permanganate anion. Again, oxygen almost always -2. So since there's 4 oxygens, there's a total of -8 coming from the oxygens. It has to add up to its charge, so -1. So what does manganese have to be? Plus what? 7, plus 7. 7 minus 8 equals -1. Great. So manganese is +7, oxygen is -2. All right, all the atoms in, what is that, calcium oxalate. But you don't have to know that. Calcium, this is an ionic compound. So this is composed of calcium 2+ and oxalate, which has to be what charge? 2-. Yeah, so calcium, that one's kind of easy, is +2, right? But the other ones are harder, right? So oxygen is always -2, yes. There's 4 of them, so I like to think, okay, there's a total of a -8 coming from oxygen. What does carbon need to contribute? But remember, it has to add up to an overall -2 charge. So I guess 2 times whatever oxidation number carbon is equals, plus 4 times the oxidation number of oxygen, which is -2, equals -2. That is algebra. So what is the oxidation number of carbon? +3. Yes, +3. And so you can check yourself, all right? Using the subscripts and the oxidation numbers, all of that should add up to 0. So calcium is +2, 2 carbons is +6, so that's a total of +8. And then there's 4 oxygens that are each 2-, so that's -8, so 8 minus 8 is 0. All right, so if you think charge, it'll get you there. Okay, so that should all be review. Okay, let's also think about other review using the activity series, right? The activity series was a way for us to predict whether redox reactions happened or not. So, or oxidation reduction reactions. So these types of reactions, single displacement reactions or redox, happens when electrons are transferred from between 2 substances. Something needs to be oxidized, meaning that it loses electrons, and something else needs to gain those electrons. That something we say is reduced. So both of these things will always happen together. A substance will lose electrons and it will be gained by another substance, the substance that's reduced. So they always happen together. And so how we determine whether something's oxidized or reduced is by looking at the oxidation numbers on the reactants and product side. So I remember electrons are negatively charged. So sometimes it's hard to think about, okay, like if the charge increases or decreases, has to do with, is it gaining or losing electrons? So I like to think if the oxidation number increases, that substance is oxidized. If the oxidation number goes down or is reduced, then that substance is reduced. So that's how I like to think of it in terms of oxidation numbers. Right? So how did we use this activity series from 1210? Well, we said a redox reaction will happen when a neutral metal is higher on the activity series than the cation. Yes, and I told you to go to sleep and say that 10 times. So you did this in lab. You put a magnesium strip in acid. You saw bubbles being formed. That was a spontaneous reaction. So if we check this out, the cation involved here is H+. So there's the cation right there. Magnesium is all the way up here on the activity series. So there's the solid, there's H+. So does that fit the criteria for a redox reaction? Yes, it does. The metal solid that's in this balanced chemical formula or equation is higher than H+. But what if we swapped it? What if we went like this? What if we put Mg2+ in with hydrogen gas? Would anything happen there? No, because now it's the metal or the neutral substance is lower on the activity series. If we swap it, it won't happen. Well, why? We just talked about chemical thermodynamics. When it was the other way, when it's this way, and a reaction happens, delta G is negative. But if we do it the opposite way, delta G is positive. So the reaction doesn't happen, right? So in chapter, the new things in that's chapter 4 review. We just think, okay, does the reaction happen spontaneously? The new ideas here in chapter 20 are, okay, why are the metals at the top easily oxidized? It has to do with reduction potentials. And, redox reactions are only spontaneous in one direction. Why? Or how do we predict it? It all has to do with delta G and cell potentials, essentially. Okay. Before you just blindly trusted me it would happen, but there's reasoning to it. All right, so let's now answer the questions. Let's look at this reaction and get the net ionic equation. All right, so how do we do that? Net ionic equation. We need to go through all of the substances and identify what? The aqueous strong electrolytes. If it's aqueous and it's a strong electrolyte, then we split it up. And then to get the net ionic equation, we can remove spectator ions. So let's think about the things that we can split. Is copper solid a strong electrolyte? No, it's not ionic, so it's not going to be an electrolyte. What about silver nitrate? Yes. Do we split it? Yes, we split it because it's a strong electrolyte, it's ionic, and it's aqueous. Do we split silver solid? No, because it's not an electrolyte. What about copper nitrate? Yes, because we split that because it is aqueous and it's a strong electrolyte. So when we write out, this is going to be the total ionic equation. So I'm just going to split the things that I indicated. So we have 2 silvers and 2 nitrates. I'm going to just drop the aqueous. We still have 2 silver solids on the product side. We have a copper 2+, and then we have 2 nitrates. All right, so do we have a spectator ion we can remove? What? Nitrate, yes, we can remove nitrate. So there's our spectator. So our net ionic equation is our total ionic equation, but just with the spectator removed. So copper solid plus 2 silver plus gives us 2 silver solids plus copper 2+. Great. All right. So what element is oxidized? So this is going to require us to write out determine the oxidation numbers, right? When we have the net ionic equation, it's usually a lot easier. So I like to just assign oxidation numbers for everything in the net ionic equation. So let's zoom in on that. Copper solid, its oxidation number is what? 0. Silver plus 1, yes. Silver solid, 0. Copper 2 plus 2, yes. So we go, we track, how does copper change? Copper solid, 0 goes to copper 2 plus. Silver plus goes to silver solid. So we track the oxidation numbers. Copper, its oxidation number is going up. So copper solid is being oxidized. Silver plus is going from +1 to 0. Its oxidation number is going down. So silver plus is being reduced. Yes, reduced. All right. And then to assign oxidizing and reducing agents, you just swap them. So since silver plus is reduced, it is also the oxidizing agent. It's the thing that is taking the electrons from the thing that is being oxidized. Copper solids, because it's being oxidized, this is the reducing agent. It's the thing that does the reducing, because something that's reduced gains electrons. Copper is giving up its electrons to reduce the other thing. All right, so there we go. I think we answered all the questions. All right, so now let's answer this. So we mixed copper and silver plus, all right, into solution based upon the activity series. Is this spontaneous? So we are mixing copper solid. Where is that? It's right here. And we're mixing silver plus. So based upon their locations on the activity series, is that reaction spontaneous? Yes. Great, because the metal is higher on the series than silver. So if you mix copper and silver plus, a reaction will spontaneously happen. But let's look at these examples. What if we mixed silver solid and copper 2 plus? So where is that? So copper 2 plus and silver, would a reaction happen there? No, so delta G is positive. Yes. What about silver plus and copper 2 plus? Copper 2 plus, silver plus. Would that happen? No. Yeah, because we have 2 ions. We don't fit the criteria. Metals has to be higher on the activity series than the cation. Right? So nothing happens here as well. So delta G should be a positive number. We're not calculating it. I just want you to relate the idea of spontaneity to delta G, because we just talked about it. All right, so what makes this chapter different? Okay, in 1210, we just qualitatively predicted whether a redox reaction would happen or not. So just qualitatively, really, you predicted the sign of delta G. That's really what you did. Right? That's what we did. So in this chapter, we're actually going to use reduction potentials and actually calculate the voltage that is produced when we mix 2 substances together that produces a redox reaction. So I want you to relate this activity series. So hopefully you got to know and love the activity series last year. The reduction potential table is actually the same exact table. It's the same exact table, but it actually has numbers, voltages associated with each of these half reactions. They're the same table. It's just this one has numbers. So in this chapter, when we ask, okay, is copper solid and silver plus, is mixing those 2 spontaneous? Yes, it is. We just looked at that because copper solid is above silver plus. What we'll see here is that the cell potential, when you add up these 2 things, is actually a positive number, right? So I want you to relate the idea of spontaneity from 1210 to, okay, let's actually calculate the cell potential. We'll calculate a positive cell potential, meaning that this reaction happens spontaneously to produce a voltage. All right, and then we can actually use this table to calculate E cell, but we'll do that later. Right? I just want you to show, oh, it's a positive number, and what we'll also get is that delta G is negative for this process. Everything's related, right? But didn't we just say, okay, when we mix silver solid and copper 2 plus, all right? So silver solid and copper 2 plus. So what's in pink here? Is that reaction spontaneous? No redox reaction will occur because the cation is higher on the activity series. So if that reaction is not spontaneous, delta G is actually a positive number. But what we actually will see here as well is that when you calculate E cell, you actually get a negative number. Yes, and so that means there's no way to get a spontaneous positive voltage, right? And so what we'll get here is that delta G is a positive number as well. All right, and so we can predict spontaneity for combining half reactions through the E cell calculation here, where we need to assign what is at our cathode, what reactions happening at our anode, and subtract those 2 values. So assigning cathode and anode is not trivial. We need to be looking at oxidation numbers. Typically here, I would put this in a red box. Reduction occurs at the cathode. Oxidation occurs at the anode, all right? So anode, N-ox, red cat, just memorize that, because that will tell you what values to put in the cell potential calculation, all right? Because it's always cathode minus anode, so we need to identify reduction and oxidation. So that's the higher level we're bringing into it in this class. So let's just do this one really quickly, all right? Here's another example of a redox reaction. This reaction does happen spontaneously, okay? Zinc solid plus H plus, so this is a net ionic equation, because if we look at the activity series, zinc 2 plus is, or zinc solid is up here, H plus is down here. So solid is higher on the activity series than the cation, right? So hopefully you can kind of quickly see oxidation numbers here. If we assign oxidation numbers at 0, +1, +2, 0, right? So if we track things, What substance is being oxidized? What substance does its oxidation number increase? Zinc, solid. What substance is being reduced? H+. What's the oxidizing agent? H+. Reducing agent is zinc solid. Now the tricky part, how many electrons are involved in this process? Look at the oxidation numbers. Yeah, 2, because zinc is losing how many electrons? 2. It's going from zinc solid to zinc 2+. So in this example, we can kind of see that 2 electrons are being transferred, all right? So in this example, it's kind of easy to see how electrons are being transferred, but it gets a little bit more complicated, which we will go over on Thursday. Okay. Oh, so we finished thermodynamics, so that means that chapter 19 homework is due on Monday.